Okay, so this topic gonna be the last topic for this semester. We are talking about the heat engines, the second law of the thermodynamics, and the concept of the entropies. So in this chapters, we're talking about the heat engines, second law of thermodynamics, heat pumps, and refrigerators, reversible and irreversible processes, the Carnot engines, the entropies, and change of the entropy in the thermodynamic systems, and finally the entropy and the second laws. Okay, so let's start with the heat engines. So a heat engine is a device, okay, that's take the energy by heat, operates as a cyclic process, expel a fractions of the energies by mean of works. Okay, so it's engines which work with what we call the working substance and work through the cyclic process. Okay, and then they do some work. So there's a few key points. So they are doing some work. Okay, they work as a cyclic process, and there is a working substance. Okay. So what happened is that the working substance absorbs the energies by heat from the high temperatures energy reservoirs, work done by the engines, and finally the energy is expelled by heat to a lower temperature reservoir. Okay, so the example of this is a steam engine which we use, for example, the water as a working substance. So this is a train, the streaming trains in the past. The water in the boiler absorbed the energies from the burning fuels and evaporated to streams, and then work does the work by expanding against the pistons. Okay. After the steam cool down and condense, the liquid water produced and returned to the boiler, and that's repeat, the cycle repeat. Okay. So with all of the descriptions, one thing that you should really consider about is what we call the cyclic process. Okay, we have learned already that what if you have the PV diagrams and then you start at some point on the PV diagrams and then it's go back. Okay, so it's mean that the change of the temperature is gonna be 0, so delta T equal to 0. So it's mean that the internal enthalpy change, it's gonna be zeros. Okay, so from the first law of the thermodynamics, we get the difference of the internal energies. It's gonna be Q plus W. So W, in our meaning, it's the work done on gas. Okay. However, in this chapter, so we're talking about the work that done by the engines. Okay, which is the so we replace W's work done on gas to the minus W engines. Okay, and it's equal to 0 because it's a cyclic process. So if we're looking on histogram, so we can see that first we need to have 2 reservoirs all the time. Right? We cannot have just 1 reservoir. Okay, for the key point. So we have the hot reservoir. Okay, and we have a cold reservoir. Okay, so the heat from the hot reservoir get into the engines, it heat. Okay, and the engine does work, and after that it produces the works, and then it give the heat to the colder reservoir. Okay, so from the diagrams, so you can see that if you just put it in this way, so start with this, starting with this one, you get Q gonna equal to the W engines, and this Q, it's Q net. Okay, so the Q net is the absolute of the Q from the hot reservoir minus absolute Q from the cold reservoir. So this is the Q net, and that Q net become work by the engines. We can talk about the thermal efficiencies. Okay. E. So what exactly is it? So it's efficiency, right? So it's mean that you get something with respect to overall, for example. So what you can define is basically the work that you get divided by the input, so the Q from the hot reservoir. And then you know that the work from the engine equal to the heat, the Q from the hot reservoir minus the Q from the cold reservoir, and then divided by the absolute of the Q from the hot reservoir. So you get 1 minus absolute QC divided by QH. So this is the statement from Kevin Planck. So this is considered also to be the second law of the thermodynamics in the way. So it said that it is impossible to advise a cyclic operating systems device, the sole effect of which is absorb the energy in the form of heat from a single thermal reservoir and to deliver an equivalent amount of work. Okay, so it's not impossible, it's impossible, right? So that you have the device that absorb the energy in form of the heat from the single reservoir and deliver an equivalent amount of work. Okay, so it's not possible that you have the hot reservoirs provide all the works and nothing else. Okay, so this is not possible. So you have to you need to have you have always have the heat out to the cold reservoir all the time. So you need at least 2 reservoir. Okay, needs 2 reservoir, right? Okay, so this is a key point of the heat engines. Okay, there are several statements that we consider it to be the second law of the thermodynamics because it can be written in a different way. Okay, you're gonna see another statement and then maybe in the way of the entropies. Okay, but first we're talking about this the heat engine first. Okay, so I give you the pictures of what we are talking about in the real situation. So we are talking about, for example, the nuclear power plants. Okay, so as you know, so you have when you see the nuclear power plant from outside, you mostly see the cooling side, so the big tank with the water vapors. Okay, but that is the side of the core reservoir. So from the hot side, you have a containment building. So inside you have the uranium fuels, okay, the nuclear fuels, and then these things can provide the heat. Okay, so you can have, and then when you have the heat, so it can boil the water. So there is what we call the stream generators. Okay, so these streams, when the stream happen, it's go to from the pipeline, okay, to turn the turbine. Okay, so to turn the turbines, so the turbines start to move. Okay, and in this case, when it's moved, it's sent to the generators and it's produce the electricities. Okay, so this is the workout. Okay, so the work, and then after that, the streams condense. Okay, and it's back to the liquid state, and then it's go back to the systems. Okay, so in this case, when it start to condense, it's produce some so so it's they have the heat transfer to the, for example, the waters. So the waters start to become hot. Okay, and then it's go as a stream to go out. Okay, So this is how it's work in the nuclear power plants. Okay, so you have two reservoirs. One is hot, one is cold, and then when the heat transfer from the hot to cold, some of the heat become works. Okay, so okay, let's start with the examples. So you have an engine which is transfer about 2 kilojoules energies of hot reservoir during the cycles, and then transfer about 1.5 kilojoules as a process to the cold reservoir. So we would like you to find the efficiencies of the engines and the how much work does the engine do in 1 circles. So let's give you a minute and try to write how can you solve these problems. Okay, so now can you work on this example? So they would like to find the efficiencies of the engines, right? So the efficiency of the engine is defined by E, and then it's equal to 1 minus the absolute of the QC divided by QH. Okay, so in this case, the heat from the hot reservoir, it's here, right? Absolute Q hot, it's here. And during a transfer of this as a cold reservoir, so this one, it's absolute of the QC, right? So the efficiency, it's divided by 1 minus Q cold divided by Q hot, right? Yeah. So you just put the numbers. So 1 minus 2 times 10 to the 3, and 1.5 times 10 to the 3. Okay, this is cancel. And then you make the numbers. Okay, that should be much simple. It's 4 over 3. So it's no, sorry, it's Q core, right? I make it wrong. Okay, so it's Q core, so it's 1.5 times 10 to the 3 divided by 2 times 10 to the 3. Okay, this cancel. So you have 0.3 4. Okay. 2, right? Yeah, sorry. I should not need this one, just 1.3 divided by 2. Okay. And then to get 2 here. So it's 0.5 divided by 2. And then you time 50. So it's 50, right? You time 50. Yeah. So you get about 25%, right? Okay. And then how much work does the engine do in 1 circles? So you need to find the works. So the work by the engines, it's equal to the Q hot minus Q cold. Okay, so you get 0.5 times 10 to the 3 joules. Okay, So this is the work that the engine does in 1 circuit. Okay, then we have first the thermal. We're talking about heat engine. So the you have the heat transfer from the hot reservoir to the cold reservoir, and then the work happens. Okay. So after, we would like to talk about the heat pump and the refrigerators. Okay. So this is another statement which also considered to be the second law of the thermodynamics. So this is statements that say that heat can never pass from the colder to a warmer body without some other change connect with occurring at the same times. Okay. So what does it mean? It means that if you have two reservoirs, it's not possible that you can heat. The heat will transfer from cold to hot without putting the work done on that. Okay, so if you're looking at the diagram, so you have the heat that you want it to transfer from the cold to the hot. Okay. However, this not happen if you don't put any work there. Okay. So this is example of the air conditioning and the heat pump, for example, or refrigerator, which is the same thing, right? The refrigerators and the air conditioning is the same thing. You would like something inside the box or in the room to be cold, and then you transfer the heat to outside. Okay, so what you would like to do, I just copy the how the air condition, the diagram that how the air condition work. Okay, so you have the room, which is this side. Okay, the heat from the room it's coming. Okay, and then you have you transfer this heat. Okay, and then this heat is transferred outside. Okay, and then it's go back to this way. And when you take the heat out from the cold side, okay, so this side that have less heat, so basically so the air become cold. Okay, so this is how the air conditioning works. If you're looking on the heat pump, it's do something slightly it's more or less the same but in the opposite way. So you would like to have a warmer place. Okay, where for example you are in snow countries, I mean in the north for example, and you put the heaters in your rooms, right? And then you would like to make the rooms more higher temperatures in that case. Okay, so in this case they take the Q, which is transfer from the outside. So the QC transfer from the outside, which is the colder, and then they are doing some work exchange. So you put the work in, okay, to bring the heat in, and then put this heat to the heaters, okay, and then after that it's returned, and then it's go back to this process. Okay, so this is how the heat pump work. So basically it's the same as the between the heat pump and the refrigerators or the air condition, just that you want the room to be hot or to be cold, and then you just switching the side of what you are trying to do. So if you would like the room to be hotter, you take the heat from outside, okay, which is colder, okay, and then you put some work to get the work done in your rooms, so the heat pass to you, and then something else go back, okay, and make the circle happens. Okay, so this is the heat pump and the refrigerators. So for the effectiveness of the heat pump and the refrigerators, it's described in the term of the COP, so the coefficient of performance. Okay, this is a similar as the thermal efficiencies. So the energy that transfer, it's a ratio of what you get basically by to what you give, right? What you get is what you finally use it, okay? And what you give, it's basically the work input, okay? It's a little different because when you're talking about the thermal efficiency, so what you get is the work, right? What you get is what so what you get is your work. What you put in is the heat. But in this case, what you get is the heat. What you put is the work. Okay, so it's slightly different in this way. So what you get, you need to answer first what you would like to get and what you have to give. Okay, for the air conditions, so we call it COP of cooling. Okay, so what you get is basically the heat that transfer from the cold side. Okay, and so what you would like to have. Okay, what you would like to have. Okay, from the cooling side, you need a cold, right? So you need to have a heat from the cold side, and for the heaters, you would like to get the heat in the hot side. Okay, so so if you ask me that what is exactly that, it's difficult to remember or not. So it's not if you can answer yourself that what you would like to get and what you have to give. Okay, and then for the heat pump and the refrigerator, you know that what you have to give is the work, because the heat cannot transfer from cold to hot without the work. So you put the work in, you get something. But for the thermal engines, the heat can transfer from the hot to the cold already. So what you would like to get is the work done by that heat engines, and what you have to give is basically the heat from the hot engines. Okay, so there's an examples of the heat pump, okay, with the coefficient of performance of 380, operates in the power consumptions of 7.03 kilowatts. Okay, so the question is how much energy does it deliver into a home during 8 hours continuous operations, and how much of energy does it extract from the outside air. Okay, so if you like to do this one, so you need to answer first what is the power in watt. Okay, and that is the one key point that you have to know, that we don't mention about it in this chapter, but the topic that you already learn about that. Okay, so it's a heat pump. So what we're talking about, it's the coefficients of the heat. Okay, so coefficients from the heat side, what you would like to get is the Q heat, right? What you would like to do, it's what you have to put in, it's work. So yeah, this is what you have. And then so you know that the heat pump have the coefficient of 3.8, so you know this term. So just do the red one, so you know this term, it's the 3.8. Okay, so how much the energy does it deliver to the home, right? So the energy that delivered to your home is the QH. Okay, so what you would like to do is basically how much of the QH, which so it's equal to W times 3.8. Okay, so W is work done. Okay, the work done is the power in the time, right? Time 3.8. Sorry, not 3.8, not 38. Okay, so you put them in 7.03 times 10 to the 3, and so the watt is the joule per second. So you convert this thing to seconds. So 1 hour have 60 minutes, 1 minute have 30 seconds. So it's 30 times 30, so 30,600 seconds. Okay, and then time 8 also, because it's 8 hours, right? And then this thing time 3.8. Okay, so let's try to calculate that. You get about 7.7 times 10 to the 8 joules. Okay, and then how much the energy does it extract from the outside air? Of course, this is the heat pump, so it needs to extract the energy from the cold side. Okay, so the cold side, it's basically the QH minus W's. Okay, so okay, so you take the QH out, so it's going to be 1 minus W divided by the QH, which is the W divided by QH is 1 over COP. Okay, so you know COP already, you know the QH already. So you place it in, and finally you will get the answer 5.767 times 10 to the 8 joules. Okay, then we move next to the, before we starting the concept of the Carnot engines, and then we go start from that one, develop the entropies. So we first talk about the reversible and the irreversible process. Okay, if you remember, when we talking up on the first law of the thermodynamics, we define what we call the quasi-static process. Okay, so the quasi-static process is that the process in equilibriums, and you can define measuring the macroscopic property of that. Okay, just to remind that when you have the PV diagrams, okay, basically you can write at the beginning and at the end. Okay, but along the way you can make a line or a dot. It depends on how you make the process happen. For examples, you compress it quickly, so when you do it quickly, at each step you cannot really measure the macroscopic property of your systems, of the gas systems. Okay, so it's not possible to say that what is the temperature, what is the pressure, what is the volume. It's happened very quickly, so so it's not the same in all the areas, for example, in that case. So you cannot measure that. What you can do is, if you need to change it slowly, so in that time you say that you put a grain of sand one by one to the system, or you remove it out one by one, so you can increase the pressures or reduce decrease the pressures. Okay, so that ideas develop also to the concept of the reversible and the irreversible process. So in the reversible process, the system is undergo and the process can return, okay, to the initial conditions along the same path. Okay, so it's mean that if you have the PV diagram and you have the path, so if you move here, you can also go back, okay, somehow. Okay, so and then at every point along the path, it is in the equilibrium state. Okay, so it's mean that you can define the state parameters clearly. Okay, if the process is not satisfy this requirement, it's what we call the irreversible process. Okay, so the concept is, you see what is a irreversible process? It's the process that not satisfy the reversible process. The reversible process means that the process that can return back on the same path, along the same path that it's evolved. Okay. All of the natural process are known to be reversibles. Irreversibles. Okay. So for example, you start with tank of gas, that gas only in one side, and then you start turn and the gas flow to the another side, and then it's never go back to one tank or again. Okay, so it's not possible that you can reverse the process to the origins. Okay, and this is the concept of the entropy that we can develop it at the next times. So the last time we're talking about the entropies. So if we would like to consider the process to be reversible, so how can we do? So it's the same concept as we has done before. So if you move slowly, so you put a grain of sand out one by one, or put it in one by one. So this process, it's reversible. So you put one grain of sand, weights, measures, put the dot in the PV diagram, put another grain of sand, weights, measure, and do it like this. So it's happened very slow, but it's mean that if you move from one point to another point, okay, you can always put if you put a grain of sand in, and then you can take it out, and the process can move it back to the to the initial states. Okay, so this is the concept of the reversible process, that how can it happen. Okay, so we're going to the one of the important topic that you should understand in this chapter, so which we call the Carnot engines. Okay, so it's considered that thing can happen as the cycles. Again, the cycle come, right? So it's mean that the process can go back to the same energy. So the change of the internal, sorry, not the same energy, go back to the same temperatures. So it's mean that the change of the internal energies become zeros. Okay. Note that the Carnot engine is a reversible process. Okay. So what's happened is first you start from the, for example, at A, and then you the system evolved by the isolated term, right? So you have the tank of gas here, okay, and then the pistons start to move, okay. However, when it starts to move, the gas, and that does the work, it needs to you need to adding some heat, okay, to keep the system to be in the same temperatures, so the isotherm. So you have the energy reservoir T hot that provide the heat to the systems. Okay, and then when we're talking about the reservoir, it means that the reservoir, the change of the energy of the reservoir, it's very small. Okay, it's very less. You can imagine that you have a sun, and then you take out some energies to boil the waters, and you say that the total energy of the sun it doesn't really change, right? It's you take a very small amount of the energies to the system that you attach. Okay, so in this case, it's gas in the piston that attached to the hot reservoir. Okay, so it's expanding, so the volume is increasing. Okay, so it's going this way. So before you develop next, okay, ask yourself, when the system is developed that the volume is expanding, so who does the work? So the gas does the work, right? Yeah, so the gas does the work. It's very important to understand that, okay? You can draw the conclusion. So if you compress it, you add the work so that the gas volume is reduced, okay? And after that, when it's reached point B, it's start to move by what we call the adiabatic process, okay? Adiabatic process, what does it mean? It means that the Q is gonna be 0, right? This is what we call the adiabatic process. So in this case, your piston it's now start to expand, but it will not exchange the energies to the environment, okay? So you have the thermal insulation installed, then the energy of the internal energy of the gas become the gas start to do the work. So the internal energy start to be reduced. So when the energy when the energy start when the kinetic energy of the gas is reduced, it means that it's go to the lower temperature. So you have the lower temperatures, a bigger volume, okay? So that's why the plot is look like this from B to C, okay? You go to the level that the volume is increasing, and then it's lower because of the temperature it's putting in this way, right? So you go to the lower temperatures, okay? So I maybe take a note first is that in this case, the W on gas is negative, right? W by gas, the work done by gas is positive, okay? And then Q equal to 0. After that, in the process C, so again, it's go to the it's go along the isothermal process, okay? So now you have the reservoir, okay? However, in these situations, you start to compress it. Okay? Not you. The system start to be compressed. Okay. However, when it start to be compressed, we would like to keep the temperature constant. So what we do is that we attach to the core reservoir. Okay. The energy of the gas is transferred from the hot side, which is the gas itself, to the reservoir, okay? So when it's transferred to the reservoir, the energy start to decrease and volume start also to decrease, okay? This balance, and then the temperature, it's, sorry, I think I speak too fast. So the heat is transferred from the hot, which is the gas, to the reservoir, which is cold. Okay, so the heat it's reduced, right? And then also the volume is also reduced, and keep the temperature to be constant. Okay, so in this case, you have the heat out from the systems. Okay, so in this figure, they write it as the Q cold, okay, which is out from the system. So in this case, you see that you have the situations where the hot Q come in, and from the first isotherm from A to B, and then from C to D, you have the heat come out. Okay. At the end, you have the adiabatic process to move from D to A. Okay, so when you move from D to A, you have the adiabatic process. What does that mean? You should have in your mind the adiabatic process that it means that you have the Q exchange between the system and the environment become 0. Okay, So you attach the thermal insulators, okay, and in this case, the so there is no heat, okay, that come. However, the volume start to be suppressed, okay. So in this case, when the volume is suppressing, so you have the delta E equal to the Q plus the W, okay, and then this the Q start to become 0, okay. So when the W is integrate P dV, right? So and we have Vf minus Vi. So if the Vf is less than Vi, so the work done need to be happens, and when the work done need to be happen, it means that it take from the internal energies, okay. So when it take the work done from the internal energies, so the temperature of the system start to decrease. Sorry, the no, I should, sorry, I think I should make it right. I'm sorry. Okay, let's start again. Sorry. So you have the okay. Sorry, I think maybe I describe it in the right way, but just too fast. So we start from the last process, number 4. So it's adiabatic, right? So you have the delta E internal equal Q plus dW. The Q's become zeros, okay. W is P dV, okay, and then V is Vf minus Vi, okay. So what you have, it's basically Vf minus Vi, it's negative, right? Because the volume is decreasing, so that's negative. So the whole overall it's the positive one, okay. So the way that the system can have bigger work done, right? So this is work done on the gas, so you need to have the work done on the gas to make its compression, so that you need to increase the internal energies, okay. So that's why it moves along the line back to the hotter temperature lines, okay. So this is the overall Carnot engine process. Okay, so I don't want you to imagine that this is the new stories. Okay, what we are trying to do is basically use the knowledge that we learn from the first law of the thermodynamics to make a cyclic process. Okay, cycle. So it's including the isothermals and the adiabatics. Okay. And then as you can imagine, this is the engine. So finally, you have the area under this curve, which is the work to go out, right? So this is the work done by the engines, okay? Okay, I think this is clear. If you start to let's say that you are start to confuse, just try to make it one by one, as I try to do for you. Okay, so you have the PV diagram. You start with this one. If you remember when you're talking about the first law of thermodynamics, so we start from Pi Vi to Pf Vf, and then we say that, okay, what happens if the volume it start to be expanding, right? The volume is expanding. It means that the gas in your system need to do the work, okay. So in that case, W on gas it's negative, okay, or W by gas is positive, okay. And then if you're looking in this diagram, you can see that at the end, at the total, and the work done, it needs to be the positive one, okay, which is the gas does the work, which is the correct thing because you are talking about the engine. You put some energy in, you want it to make the work done happen, and then as it cannot be perfect, right, by the statements, you have the heat transfer out on the cold side, so to the cold reservoir. Okay, so we're talking about the thermal efficiencies of the engines. Okay, so the thermal efficiency of the engine is basically it's the same as what we have defined before. So at the beginning of the class of this lecture, so it's 1 minus absolute of the QC over the QH. Okay, so QH is what you put, and QC is what it's out. Okay, okay, so you can do that. So we consider each of the process. So you have two isotherm and two adiabatics. Okay. So from A to B is isotherm, B to C it's adiabatics. So C to D is the isotherm, and D to A it's become the adiabatics. Okay. So what is the easiest thing that you can do? If it's this exam, for example, you can first put some numbers to these four states. Okay, so what you can put is basically adiabatics, because you already know that the Q is 0, right? Yeah, so we will not focus this for now. Okay, let's start from the A to B. It's the isotherm, right? So we would like to find the Q. Okay. However, since we consider the isotherm, right? Delta E internal equal to the Q plus the W's. Okay. So isotherm, so E start to become zeros. So the Q is minus W, and W, this is W on gas. Okay. And then you convert its unit to the Q equal to W, and this is W of the engine. Okay. Okay, so if you can find the work done, you have the Q. Okay, and you have the absolute. So if you miss the concept of the psi, it's fine, but it's better that you don't miss it. Okay. So what is the work done for the isothermal process? Good questions. We did that before. Okay, we did it in the first law of the thermodynamics. Should be this one. Nope, this one. Looking back, isothermal here. Okay, here. The minus nRT natural log VFOVI, or minus nRT natural log PI over PF. Okay. Which one you would like to use? Yeah, you can use either of that, because you have, if you know T, basically you can convert between them, right? Okay, let's take the volume one. Okay. Oops. From A to B, right? The work done. Oops. The work done, which is basically from A to B, it's the QH, right? I just maybe write it Q hot because we're talking about that. It's equal to work done from A to B by the engines, okay? Sorry, the work done. So what it's exactly it does, it's nRT natural logs of VF divided by VI. Okay, so it's nRT natural log of VF, it's VB over VA, right? Okay. You follow me? So you just use this formula, okay, and then you take VF as a VB, VI as the VA, as the process goal, okay. So next one, it's about the C to D, okay. So the Q code WC to D, okay. So it's equal to the nRT natural logs of VD over VC, right? So this is how things work, right? But remember that VD is less than VC. Okay, so VD is less than VC. What does it mean? It's mean that this thing, okay, it's gonna be log of you can take VC over VD, and then you take the -1, okay, and then you take the minus out, okay. Just go to here. You understand? Yeah. So you take, for example, I can just give the number so that you can just a second. Okay. Let's give some examples by numbers. It's maybe not precisely, but this is how things done. So if you have, for example, the natural log of 1/3, right? Basically, it's natural log of 3 to the power of -1, and you get -1 natural log 3, okay? And this one, it's 1 point something, okay? So if you calculate in the calculator, you can use this one or you can use this one. It's the same. However, in this situation, we consider in the absolute way, okay? So we can make take the -1 out, okay. Why it's have the minus here? Because basically you move from the large volume to the small volume. So it's mean that in this process, okay, the gas doesn't work. There's some work need to be done on the gas, okay, which is the right statement, okay. So basically you can write it in the positive way. So you have the nRT natural log VC over VD, okay. So at the end, you're gonna have efficiencies. So 1 minus, I remove take the nRT. I'm sorry, nr, not T. So the T is, this is T hot, this is T cold. So I take only the nr out, cancel. Okay, so you have QC, so which is TC over TH. Okay, and natural log of VD, VC over VD divided by natural log VB over VA. Okay, so we have this one. Okay. So it's look okay. Okay, if you have the calculator, you just press it, which is fine. But the question is then how can we make it more simple? Okay. So TC and TH is something that you measure it, right? So it's a hot and cold, the temperature of the cold and the hot reservoir. So what you would like to do is maybe you can try to let's say play with this term a little more. Okay, so what is the value of the natural log VC over VD divided by the natural logs of the VA over VB over VA. Okay, so if the what we would like to find is equal to 1, it's everything is gonna be simple. So the efficiency is 1 minus TC over TH. Okay. Before we prove this is a real statement or not, I would like you to focus first on the meaning of the efficiencies. Okay. So for the meaning of efficiency, you can see that at the end, it depends on the hot and cold temperatures. Okay. So what does it mean is that if you have the Carnot engines, okay, the efficiency, it's depend on the hot and cold reservoir. If you have hot and cold reservoir, which is the same temperatures, you can get the same efficiencies for all Carnot engines. Okay. So the efficiency of the all Carnot engines, the efficiencies of the Carnot engines can also imply that all Carnot engines have the same efficiency if they have the same T hot and the T cold reservoir. Okay, so it's depend on the temperatures. Okay, so we go back that if you can prove that natural log of VCO over VD divided by the natural logs of VB over VA, it's 1 or not. Okay, so how can we prove that? We can go back a bit and you can see that we already use the relation of the work done in the isotherm, right? We still have another key point, which is the adiabatics. Okay, so let's start to think about the adiabatics. So you can link between the point B and C and point A and D. Okay, so link from the adiabatic process. Okay, so look at the considers. Adiabatic process. Okay, in the adiabatic process, what we have learned before, this is adiabatic process. Okay, so we have TF, right? TV to the power R over CV become constants. Okay, so this is what we have, right? TF, this I'd like to use this one. So TF, VF to the power of R over CV equal to the TI VI R over CV. Okay, so we can write TV, right? TV R over CV equal to the constant Okay. So what is the process? We have from B to C, right? From B, which is T hot, to C, which is T cold. Okay. So we can have T hot, VB R over CV equal to the T at C. So T cold, VC over CV. And then we have from D to A, right? We consider from B to C, and then we now consider from D back to A. So VD it's T cold, VA it's T hot. So we have, I put the T hot in the same side. So T hot VA over CV equal to the T cold VD over CV. Okay. So you have two equations from the adiabatic process. So if you do 1 divided by 2, okay, 1 divided by 2, so T hot can cancel, T cold cancel. Then we have our CV cancel to each other later. So you have VB over VA equal to the VC over VD, right? VOA V over VA equal to the VC over VD. Okay, this is what we ought to have. So VC over VD, it's equal to the VB over VA. So we put it back here. So it's become natural log of VA, VB over VA. Okay, so then this log cancel. So you get 1. Okay, so you can prove now that the efficiency is equal to the 1 minus Tc over Th. Okay, so now you have this formula. Okay, so we finally going to the next step so that we can calculate the efficiencies from the Carnot engines, and we learned that the Carnot engine the efficiency can be described by the just two temperature, hot and cold. Okay. So we can also calculate the coefficients COP of the Carnot engine. So you subscribe by C. So the heat one, of course, you take the same formula. So absolute QH divided by the work. So you get the TH divided by T hot minus T cold, and the COP of the cooling QC over the W. So it's equal to the T cold divided by T hot minus T cold. Okay, the example before we finish this recording, and then we're gonna continue the remaining topic in the next recording. So in this example, so we have a Carnot engine has a power of the 150 kilowatts. The engine operates between two reservoirs at the two temperature 20 and the 500 degrees centigrade. Okay, so the question is how much energy entered to the engine by the heat per hours, and how much energy is exhausted by the heat per hours. So from the problem, you have the T hot, okay, which is 500 times 273 Kelvin. You have T cold equal to the 20 and 273 Kelvin. Okay, so the efficiencies, okay, we link the efficiency. So you have the two efficiencies. So you have the efficiency of the Carnot engine. So T 1 minus TC over TH, right? This is how you calculate. And then for the power output, we have another efficiency that we used before, because this is the hot engines, right? So we can use the same concept that we developed before. So the thermal efficiency is the W engines divided by QH. Okay. So you have the W of engines divided by QH. Okay. So now you have in the problem it said the power output, right? So it's mean that the work done in the time. Okay. So you divided by the delta T, and then you divided here by the delta T. So the top one can become the power. Okay. And this one gonna be per hours that we use here. Okay. And how much of the energy entered to the engine? It's this one. Okay, so you link what you have already. Okay, so what you have to do is just arrange the equations. So what you should do is EQH, right? It's gonna be P, which is here, times delta T, which is coming from this one, right, divided by 1 minus TC over TH. Okay. So you have all the numbers, just put it in. It's about, we should get about 8.7 times 10 to the 8 joules. Okay. And then how much of energy extracted by the heat per hours? So since you already calculate the heat that enter to the engines per hour already, so you have QC equal to the QH, right? The minus the W engines, right? Okay, so the one you have it's the QH minus P divided by the delta T. Okay, so the no, the power yeah, okay. Oh, sorry, not divided. The delta T. Okay, so this become power. It's become what? Sorry. Then you can calculate that. Okay. Right? Yes, I do it right. So the W, so it's equal to the P time with T time. Okay. You get the 3.3 times 10 to the 8 joules. Okay. Did I get something wrong? Yes, it's correct. No, sorry, just confused on what I put about the P. So the power, it's basically the watt per hour. Sorry, the work done per unit time, right? So if you'd like to get the work done, so you take the power and multiply it by time. Okay, so this is what we have used here and what we using here. Okay, So I think we stop here. Next, we're gonna talking about the Carnot principles that gonna lead to the entropies, and then we're gonna discuss about the concept of the changing of the entropies. Okay, at the last topic of these chapters. Okay, it's gonna very close to the exam. Just try to spend your times on the on the subjects. Okay. Okay, this is all for today. Thank you and see you at the next recording.